Moving on to example 2, we are going to learn about iterative techniques. And we are going to have to use an iterative technique because in this problem, we are interested in determining the final temperature of 15 kilograms of carbon dioxide that undergoes a constant pressure heating process for an initial temperature of 25 degrees centigrade to an unbeknownst temperature. All we know is we receive 10.2 megajoules of heat during this process. And to determine our final temperature, we are going to look at 4 methods. The first is to treat our constant pressure specific heat as a constant taken from table A5. The second is to treat our constant pressure specific heat as a constant evaluated at the average temperature using a polynomial expression from table A6. Our third method is to treat our constant pressure specific heat as a constant evaluated at the average constant pressure specific heat using our polynomial expressions from table A6. And our last method is treating our constant pressure specific heat as the integral average evaluated between our initial and final temperature using our polynomial expression from table A6. Part A is going to be relatively easy since CP is a constant. Parts B, C, and D are going to require an iterative technique. Let us first begin with part A. In this solution, we're going to use MATLAB. Our first statement is clear all. This clears all the variables within our workspace. Our second statement, CLC, clears our screen. Now we have givens. The first is we have a mass of 15 kilograms. The second is our initial temperature is 25 degrees centigrade, or 298.15 Kelvin. And our heat supplied is 10,200 kilojoules. Now from table A5, our CP0 for carbon dioxide is 0.842 kilojoule per kgK. And we can solve our temperature at state 2 by taking our heat supplied per our mass times our constant pressure specific heat plus our initial temperature. In doing such, we find our temperature at state 2 to be 1105.75 Kelvin. Now keep note of this value. We are going to use it to initialize our temperature for part B. Part B, we are going to reproduce our code. First of all, we're going to clear all variables and clear our screen. We have our same givens of mass, temperature, and heat supplied. Now consulting table A6, we need to pull C0, C1, C2, and C3. C0 is equal to 0.45, C1 is equal to 1.67, C2 is equal to minus 1.27, and C3 is equal to 0.39. Now we're going to construct a function for our constant pressure specific heat. Our function, Cp, is equal to at parentheses x, and x is our input. Recall our input for using our polynomial expression on table A6 is theta, which is our temperature divided by 1000. And Cp is equal to C0 plus C1x plus C2x squared plus C3x cubed. Now, for us to determine the solution, we first must initialize our temperature. That is, we're going to guess a final temperature. That is T2 old. This will be our initial guess, and we will take the temperature from part 1. We will say T2 old is equal to 1105.75 Kelvin. Next, we're going to define error. Now we'll define a while loop. While our error is greater than 1 e to the minus 5, we can solve the following system of equations. Firstly, we're going to calculate our average temperature. Our average temperature is T1 plus T2 old per 2, where T2 old is our assumed final temperature. Theta is our average temperature divided by 1000. T2 new is equal to our heat supplied per our mass times our specific heat, which is a function of theta, plus T1. We'll define error as the absolute value of T2 new, which is our final temperature we just solved for, less T2 old. Now we'll redefine T2 old as T2 new, such that the temperature we just calculated will initialize our equation for T average, and we'll repeat this process. Once our error is below 1 e to the minus 5, this loop will break. If we execute this, after 11 iterations, we arrive at a final temperature of 924.63 Kelvin. Now, for part C, we are going to repeat most of our problem statement. We're going to have our givens, we're going to have C0 through C3, and we're going to have an expression for our constant pressure specific heat as a function of theta, i.e. our variable x. Now, we're going to initialize our system. T2 old is going to be equal to 924.63. This was from part B. Once again, we'll have an error tolerance. Now, while our error is greater than 1 e to the minus 5, we will calculate our specific heat based upon the average of our specific heat evaluated at T1 and our specific heat evaluated at T2. That is, theta 1 would be T1 per 1000, and theta 2 would be T2 old per 1000. Our specific heat corresponding to T1, CP1, is CP theta 1, and our specific heat corresponding to T2, i.e. CP2, would be CP of theta 2. Now we can calculate our average specific heat, CP average, by taking CP1 plus CP2 per 2. Now our final temperature, T2 nu, is equal to our heat supplied per our mass times our average specific heat, CP average, plus T1. And once again, we define our error as our newly calculated value, T2 nu, less our old value, T2 old. And then we reinitialize our system by calling T2 old T2 new. If we execute this, we find that T2 nu is equal to 954.67 Kelvin. And it took 8 iterations for us to arrive at the solution based upon our error tolerance. Last but not least, part D is where we want to use the integral average. Once again, we are going to repeat our givens, our C0 through C3 values, as well as now a function for the integral of CP. We define CP int as the integral of CP. That is, it is still a function at x, but now we are going to integrate it with respect to temperature. And to do that, recall CP was a function of theta, so we have to convert from theta to temperature. Therefore, CP int is equal to 1000 times C0 times x plus C1 per 2 times x squared plus C2 per 3 times x cubed plus C3 per 4 times x to the 4th. And we'll repeat the same methodology. Now, we're going to guess our initial temperature. We're going to find T2 old as 954.67, and we took this from part B. Once again, we define our error, and we'll construct a while loop. While our error is greater than 1 e to minus 5, we have the following. Theta 1 is equal to T1 per 1000. Theta 2 is equal to T2 old per 1000. And the change of our enthalpy is equal to CP int evaluated at theta 2 less CP int evaluated at theta 1 per our temperature difference. Now we can calculate T2 nu. T2 nu is equal to heat supplied per our mass times our change of enthalpy plus T1. We define our error as our newly calculated value less our old value, and then we reinitialize our system. If we execute this statement, we see our final temperature is 933.96 Kelvin, and it took 9 iterations for us to arrive at this value. Now we see as we progressed with better expressing our constant pressure specific heat, i.e. we went from a constant, evaluated at 25 degrees centigrade, we took it as a constant value, evaluated at our average temperature, we took it as a constant based upon the average of our CP evaluated at our starting and final temperatures, and then we did our integral average. We saw as we increased in complexity, we matched more closely the solution we get by pulling tabulated values from our table.